In this video, we show how to use induction to prove that the grammar such that the language of the grammar is L is unambiguous, where L, our language, is the set of strings W over alphabet A, B, such that the number of A's in W is equal to the number of B's in W. So we showed how to think about creating this grammar in a previous video, and so we have a candidate grammar for testing or proving that it's unambiguous, and that's what we're going to do via induction. So first, let's remind ourselves what our grammar is. Our grammar, let's call it G, is going to be the rules E goes to A, big A, B, E, or B, big B, A, E, or epsilon. And we have variable A goes to little a, big A, B, big A, or epsilon. And B goes to little b, big B, little a, big B, or epsilon. Okay, so there's our grammar. Okay, so we want to prove that G is unambiguous. So we need to prove that any string derived from G has only one leftmost derivation. We know that strings are terminals, so we're talking about strings of terminals, so strings are a string of terminals, and strings are derived from variables, right? So if we can show that for any string W, so this is what we want to do. We want to show that for any string W derived from the variables E, A, and B, W has only one leftmost derivation. Okay? This says that W has only one leftmost derivation in the grammar. Why? Because if it has only one leftmost derivation from E, the start variable, then it has only one leftmost derivation in the grammar. That's basically what that means, right? All strings are derived starting at E, so if we can show that there's one leftmost derivation from E, then we get that there's only one leftmost derivation. Why do we have A and B here? It's going to make it easier for induction to prove that for every variable there's only one leftmost derivation, and then we can put all of these variables together. Since A and B are, we get to them from E, they're in a derivation from E, then if any string generated or derived from A has only one leftmost derivation, any string derived from B has only one leftmost derivation, and any string derived from E has only one leftmost derivation, then there's only one leftmost derivation for that string in the grammar. Okay, so that's what we're going to do. And we're going to do a proof by induction. So proof by induction. And remember that whenever you're doing a proof by induction, you have to do induction on something, okay? So we're going to do a proof by induction on the length of W. Okay, so first let's handle our base case. Okay, so what's our base case here? It's going to be the shortest string we can make, right? That's usually what a base case is what's the first you can do. So the shortest string that we can make has length 0, right? And this is when W is epsilon. Okay, so how can we prove that there's only one leftmost derivation on any of the variables when the length of W is 0? Well, let's try for E. Okay, so if our derivation, if we're deriving W from E, okay, if we take any rule other than, so let me pop back to our grammar, if I take the first rule from E, so A, big A, B, E, I'm not going to get epsilon, right? I'm going to have some A's and B's in there, so W is not going to be epsilon. Same thing with the second rule. So the only rule I could have used was E goes to epsilon. Okay, so if E yields in one or more step W, which is epsilon, then it must be the case that E directly yields W. It's the only rule we can use. And when we're doing only one replacement, there is necessarily one leftmost derivation, right? There is no other variable to replace. So that's my leftmost derivation. Okay, and the same is going to be true if A yields W in 0 or more steps. It must be the case that the rule we used was A goes to epsilon, and therefore there's one leftmost derivation. Okay, same thing for B. Oops. Okay. So this handles our base case when W is epsilon. We always have a leftmost derivation from any variable to epsilon. Okay, so our inductive hypothesis says we're going to assume that for each W, which is an element of AB star, okay, so it's in our sigma star, with the length of W being equal to n, where n is going to be greater than or equal to 0. Remember, our base case handled 0. And now we're going to handle, with our inductive hypothesis, anything from 0 up to n. Okay? We don't know what n is, but we say up to some value n. W has, at most, one leftmost derivation from E, A, and B. Okay, notice just as a subtle point here, we say W has at most one instead of exactly one. Our condition here was that W is just a string over the alphabet. We didn't actually say that it's a string in the grammar. Okay, so that's why that subtlety is there, at most one. Okay, so that's our inductive hypothesis. Now we can move forward to our inductive step. Okay, so we are going to break, so let me put inductive step here. Okay, we're going to break our problem into 3 cases for our 3 variables. We're going to handle independently. And we're going to show that the inductive hypothesis holds for length of W equal to length of W is equal to n plus 1, where n itself is greater than or equal to 0. Okay, so here we don't know what n is. It was some n that we had in the inductive hypothesis. So I'm just making a note here that n has to be at least 0, and so length of W is going to be at least 1. Okay? But we don't know here, again, what n is. It's whatever n we get from the inductive hypothesis. So, case 1. In case 1, we're going to handle from A. So we want to show that for each string W derived from A in 2 or more steps, so A yields W, there is a unique leftmost derivation of w from A, which we're going to write A yields using a leftmost derivation w. Okay, notice that I said here, even though this symbol, this A with the arrow and the star w means yields in one or more steps, I actually said yields in two or more steps. Okay, this is a subtlety because the base case handled when A yields w in one step. Okay, remember here when we said that if A is going to yield w in exactly one step, it must be the case that w was epsilon, right? Why is this? Any other rule in the grammar is going to produce additional terminals but also additional variables. Okay, so if A yields w in two steps, it must be the case that I used A, B, big A, and then possibly, and then after that maybe epsilon for the A. Okay, so point is, if I'm yielding a string in exactly one step, the string has to be epsilon. Okay, so I'm really only concerned with at least two steps. Okay, so back to case 1. So we're showing that for each string yield from A, there's a leftmost derivation from A, a unique leftmost derivation from A. Okay, so what is our proof? Okay, so what do we know? We know that A is going to yield something that looks like this, right? Because I said we can't use the A goes to epsilon rule here because the length of w is not 0. So we have something that looks like this. It's going to use this rule, the non-epsilon rule, and then do some other stuff and eventually yield w. Okay, then we can replace the first A with a string y. Okay, this is the A we're talking about. Okay, so then what do we have? Steps along our derivation are going to look like this. Okay, so now let's consider how we got to y. So we're going to consider A yielding y. Okay, so what I'm talking about is how we made this replacement to get from there to there. Okay, we know that the length of w is equal to n plus 1. Okay, that's what we're showing, when the length of w is n plus 1. Then we know, so here's our w. W has an A, a B, a y, and then something else generated by this big A, right? So we know that the length of y has to be less than or equal to n minus 1. How can I say that? The length of w, I'm going to say because length of w is equal to n plus 1. Okay, length of w is n plus 1. It has at least an A and a B in it that's not part of y, so that's 2 of my characters right there. So y is at most n minus 1 length. Okay, so then according to the inductive hypothesis, remember that the inductive hypothesis gave us a leftmost derivation for any string from a variable when that string has length up to n. Okay? So y has length less than n, so y is covered by the inductive hypothesis. So this tells us that y has a unique leftmost derivation from A. Okay, so what we write here is A is going to yield via a leftmost derivation, a unique leftmost derivation, A, y, b, A. Okay? And so now let's plug this into the derivation we have running for W, so we know A is going to yield via a unique leftmost derivation A, Y, B, A, and then W. Okay, so what does all of this actually mean? It means that we've handled the first part of the string W, and we've said this first part of the string W has a unique leftmost derivation from A. Okay, so now we need to handle the second part of the string W, everything generated by this A. Okay, how are we going to do that? We're going to replace the second A, second variable A, with the string Z. Okay, so what do we have then? Our running derivation looks like this. Here was our step where we had to take this rule instead of the epsilon rule, right? Then there's a unique leftmost derivation to replace the first A with Y. Okay, and then we know we're doing something here to get to Z. Okay, and here I only have terminals at this point, so this must be W. Okay, how do I know that? Because I'm constructing this proof by basically dissecting W into its components. Okay, and we'd handled A, Y, B before, and now we're saying, okay, let's see what this variable A here, what this one could generate. And what does it generate? It's going to generate something Z, right? It has to replace all of the variables with terminals. Let's call that string of terminals Z. Okay? All right, so now what do we know about Z? Well, again, we know the length of W is n plus 1. Y could be empty. We haven't stated that it's not, right? Which means that if the length of W is n plus 1, the length of Z is at most n minus 1, right? So we have length of Z is less than or equal to n minus 1. We know this. Okay, the hypothesis holds for Z as well. It held for everything up to n. Z is no more than n, for sure, so the inductive hypothesis holds. What does that tell us? It tells us that Z has a unique leftmost derivation from A. Okay, then let's plug this back into our running derivation for W. So then we have A is going to yield the leftmost derivation ABA, and I could have had this here, right? There's one way to do that. Okay, and then what do? We have a unique leftmost derivation using the first A to get Y. Okay, and then we show there's a unique leftmost derivation from the second A to Z. And this string was W. Okay? So let's look along our chain. Everything in our chain has a unique leftmost derivation. Okay, so at no point could we have generated W from A in any other way using a leftmost derivation. Okay, so this tells us if therefore A yields W using a unique leftmost derivation. Okay? So now, let's move on to case 2. So we've handled variable A. Now we need to handle variable B. Case 2. For each string derived from B, there is a unique leftmost derivation from B. Okay, this is going to be very similar to the previous proof. For A, again, we're going to remind ourselves that we've already handled the case where when this is handled in one step. That is, B goes to W in one step, which means that W has to be epsilon. That was handled by our base case. So here we're considering that B goes to W, B yields W, excuse me, in at least 2 steps, which is going to require us to use the other rule. Okay, so what we have here is that B is going to yield using the other rule, little b big B, little a big B, and this yields in some number of steps W. Okay, let's replace first variable B, so I'm talking about this one, with string, let's call it U. Okay, so what do we have? We have that B yields little b big B. And remember, this is leftmost. I can actually start saying this right away, right? There's only one variable B to replace. It must be leftmost, and it must be a unique leftmost derivation. Little b big B, little a big B. And then we have, in 0 more steps, we get little b U, a big B. Okay? And then in 0 more steps after that, I'm sorry, not 0 more, in some number of steps after that, we're going to get W. Okay? So we want to know what do we have in terms of getting from this B to this U. Okay, so that's what we're considering. Okay, what do we know? The length of W has to be n plus 1, so the length of U has to be less than or equal to n minus 1. So then, so we have, since length of U is less than or equal to n minus 1, it's handled by our inductive hypothesis. So there's a unique leftmost derivation from B to U. So we have, using our notation, unique leftmost derivation from B to U. Okay, then we have, plugging this back into our derivation, okay? Oops. Yeah, now it's okay. Okay. So we've handled the first chunk of W. Now again, we're going to handle the second chunk of W. We are going to replace the second variable, B, with some string, let's call it V. Okay, so what do we have? Let me make that cleaner. So we had B-U-A-V, and this is going to be equal to W. Why? Because we're down to only terminals, so that must be W. Okay, so now for the same reason, since the length of V is less than or equal to n minus 1, the inductive hypothesis holds for the derivation from B to V. So we have, there's unique leftmost derivation from B to V. Okay, so let's plug this back into our ongoing derivation for W. We had a unique leftmost derivation to get from B to little b big B, a big B. We had a unique leftmost derivation for the replacement of big B by U. We have a unique leftmost derivation for the replacement of big B by V, and this was our string W. So that we can see that W is uniquely generated by leftmost derivation from B. So we can conclude there's unique leftmost derivation from B to W. Okay. we have now handled case 2. Okay, so this is our conclusion for case 2. So we've got unique leftmost derivation on any string from A, a unique leftmost derivation on any string from B. So now we need to handle from E. 3. And what we want to show is show that for each string generated from E, there is a unique leftmost derivation from E to W. Okay, so here's our proof. Let's assume that we choose the rule. Assume we use the rule E goes to little a, big A, little b, E. Okay? If E, which then yields A, big A, B, E, and then in some other number of steps W, we're going to replace the first A, so this one, to get string X. Okay, so what does our derivation look like? E goes to A, big A, B, E. And actually I should start filling this in right away. This is a leftmost derivation, a unique leftmost derivation. Okay, because it's done in one step, it's uniquely leftmost. We can't take any other rule or any other sequence of rules to get from E to this. Okay, so then we replaced the first A with X, some string X. Okay. So now let's think about how we could have gotten from A to X. So we're going to consider A yielding X. Okay, in case 2, we proved that there exists a unique leftmost derivation for A yielding X. Okay, so we have that A has a unique leftmost derivation to X, or X has a unique leftmost derivation from A by case 2. Okay? Then let's go back to our running derivation, E via leftmost derivation, A, B, E. Okay? Via unique leftmost derivation. I'm not really, that's, yeah. Let's try to make that look like actual letters. There we go. A, X, B, E, and then some other number of steps to get to W. Okay, so now we want to consider replacing E, okay, this one, this E, with string T. Okay, so what is this going to look like in our running derivation? We're going to have E leftmost, A, big A, B, E. Via unique leftmost derivation, we get A, X, B, E. Okay, and then we're wondering what happens from A, X, B, oops, from E to A, X, B, T. Okay, we're down to only terminals. This must be W. Okay, so what do we know about the length of T? Well, we knew the length of W was equal to N plus 1. Therefore, the length of T has to be less than or equal to n minus 1, right? Because the a and b characters there ate up 2 characters in the length of w, so if w is n plus 1, t can't be more than n minus 1. So we have, according to our inductive hypothesis, we're going to have a unique leftmost derivation from e to t. So this is via inductive hypothesis. We have a unique leftmost derivation from e to t. Okay, remember that we handled this in our base case. Well, we handled e going to length 0, and then our inductive hypothesis handled, so this is what I'm trying to say, our inductive hypothesis. So any length w equal, any string with length n from e, a, or b. So we handled length up to n for variable e. Okay, so that's how we get to use our inductive hypothesis to show that since t has length less than n, there's a unique leftmost derivation from e to t. Okay, so let's plug this back into our running derivation to see what we have. Okay, and we knew that this was a unique leftmost derivation to replace e with t. Okay. So what did we just show? We showed that if e gets replaced by the rule a, big A, B, E, we have a unique leftmost derivation for E yields W. Okay? So if rule E goes to A, this is used, if this rule is used, then E has a unique leftmost derivation to W. Okay, so that's one of the cases. What's the other rule we need to use? What if we use, if rule E goes to little b, big B, A, E is used to get W? Well, we're going to have the exact same argument we just had, except that we're going to replace A with B. So in this step, right here, oh, did I say case 2? I think I meant case 1. That was case 1, right? Where we did A. So right here, where we're doing this part, replace that with B goes to X. Then formulate the same argument, go through the steps, show that if we replace B with X, and then we replace E with T, we get a unique leftmost derivation. And this one would be by case 2, actually by case 2. So I'm going to just say similar argument to above. Okay, what does this give us? We can conclude there's a unique leftmost derivation for every string W in the language of the grammar. Okay? So convince yourself that this works. Remember the 3 parts of induction? We had our base case. We showed for the smallest possible value, for 0 in this case, length of 0. Then we had our inductive hypothesis where we said, okay, we'll assume that our hypothesis holds for every string up to length n. And then let's show that if that was true, that it would hold for the string with length n plus 1, right? And so we go through the steps. We show how to apply the inductive hypothesis for every string with length n plus 1 using breaking the string of length n plus 1 down into pieces that are less than n. And because we did that, our inductive hypothesis holds for those pieces. Okay, then we pull it all together, and we showed that our conclusion is true for any length, right? Because if I can get to length n plus 1, and it's true for that, then I can get length to n plus 2, and n plus 3, and n plus 4, and we can keep building forever. Okay? So that's it.